thank you for introduction. And yes, so I'm Hiroshi Rata, and I'm a data scientist. And also, like, I've been contributing machine learning in Tokyo for, I think, 1.5 years, or more than one year and a half. And I think this is the fourth presentation, my first presentation at MLT. Then, yeah, so I think this session, I think participants are from all over the world, but in Tokyo, now it's super hot. So I think that's why it's better to stay inside to study mathematics. So with us, so yeah. Okay, let's get into the topic. Yeah. Today I will explain about principal component analysis. And actually, I already explained in the first session. But those are really basics. Then today I'll explain more detail. However, I think like I will mainly focus on linear algebra. So actually, I like to review. There's some like topics of the linear algebra, so which is really important behind the scene of principal component analysis. So yeah, I'll be glad. So if you enjoy my presentation. So okay. Okay. Okay, then let's get started. Wait a moment. Okay, so can you hear me?
Yes.
Okay, so first of all, I'll explain about I will review what I explained in a previous session about the principal component analysis. Yeah, so in a probabilistic approach of the principal component analysis, so we always think about the generative process of the data. So that's why, first of all, we think about the observations, so data itself. So let's say here, it's X represent the observation. Let's say this is the dimension. Also, principal component analysis is latent variable model. Therefore, the latent variable is required. So let Z represent the latent variable. Let's say M dimension. So then, as I have explained in the previous session, we assume the probability distribution for each variable. I think, I hope everyone is familiar with this notation. This is a normal distribution with mean is 0 and covariance matrix is identity matrix. Yeah. Then also the distribution of X given Z. So the interesting point is in a probabilistic principal component analysis, we assume, first of all, the Z in a latent space, the data was observed, sampled, and that sample is transformed with matrix. Then the observations are sampled. These are basic mechanism of the probabilistic principal component analysis. Yep. Let's say, so matrix is W here. Yep. So this matrix is D by N. Yeah. Because Z is M dimension. So that's why D by M dimension. Then we obtain the D dimension vector as a mean of the distribution of X given Z. Yeah, that's how it works. Yep. Then also this means is so covariance matrix. However, the matrix is a isotropical matrix with sigma squared. Yep. These are the model. So basic model of the probabilistic principal component analysis. Then, as I have said, in a probabilistic approach, the generative process is really important. So therefore, I'll explain about the generative process in a really simple case. Let's say the observation is 2-dimension. Then the latent space is only one dimension. In that case, the distribution of Z is obviously just that's a normal distribution. So sorry, my handwriting is not good. So yeah. Then as I have said, for generative process in a probabilistic principal component analysis, first of all, Z is sampled from this distribution, this one. That's why, let's say we got the sample here, then so we apply the linear transformation here. Linear transformation W. Now, because D equal 2 and M equal 1, so therefore W is 2-dimension. Oh, two-dimension vector. Yeah. Then let's say W is this direction. So then because the transformation is W and Z, so that's why, for instance, Z is, let's say 1.5 was sampled from latent space, and let's say W WZ is this vector, which has 1.5 times length of W. Yeah. then there is a variance of isotropic. That's why we'll sample from like this kind of contour. And that's why sample will be here or here, but something near the mean of WZ is expected, maybe. Yeah. Then also another sample is here. And this is a little minus, right? So that's why WZ is maybe here. Then with variance, we sample here or a little, distant from mean. Then that's how we sample lots of data. Then data will distribute it like this. So as a result, if Z is marginalized, then distribution of X will so multivariate Gaussian distribution. So this distribution indicates this distribution. Yeah. Then I think someone might wonder why the okay. So before that, I think this is the basic idea of probabilistic principal component analysis. Yeah. Then also like someone might wonder, so why this is 0 and the covariance matrix is this. So that's why like I'll explain a little bit. So, okay. First of all, mean is I think that's this is a kind of review of the calculation of expectation and variance. Like, yeah, that's a basics of the statistics, I think. Yeah, so here. So the X is here, in this model, Z X is WZ. And also there's a variance. So that's why like I just like written epsilon. Then actually expectation has linearity. That's why we can write like this. That's why 0 plus 0 equal 0. Actually, expectation of Z is 0. Described here. Yeah. And also, okay. The next I will explain the covariance matrix of X. Oh. I hope you remember how covariance is computed. So there is a, let's say, this is just a little bit preview. Let's say X is the probability variable. Then covariance can be computed. This is the basic idea. Now, the mu x means expectation x, then so as I calculated it, expectation of x is 0. Yeah, therefore, so therefore we can write this. So then you can calculate. I think it's a 2. There's not much space. You. Yeah, these are the review of statistics. Then, so you can calculate like this. Yep. Yeah. These are the basic calculation of matrix and vector. Then again, we can apply the linearity of expectation. As a result, so this is the covariance matrix of Z, right? Then covariance matrix of Z is just identity matrix. That's why. Yeah. Also, epsilon, the covariance matrix of epsilon is identity matrix with sigma squared. This is 0. Yeah. So as a result, now, so we just calculated the covariance matrix of X and mean equals 0. That's why the distribution Px is like this. So multiply it normal distribution. So that's how it's derived. Yeah. So so these are the review from the previous session. So these are basics of principal probabilistic principal component analysis. So then today I want to talk about the invariance of the. So one of the characteristics of the probabilistic principal component analysis is the invariance. Then I'd like to talk about that. But before that, I'd like to introduce the orthogonal matrix. So today I'll explain about the property of orthogonal matrix. So I think that will be a good review of the linear algebra. Then the property of orthogonal matrix is key role for invariance of PPCA. That's how I'll explain about it. That's why, first of all, I will explain about orthogonal matrix. So yeah, because of the Zoom event, so it's really quiet. So yeah,
we're here. We're patient.
Thank you. Okay, so yeah, so orthogonal matrix is the square matrix. Then where so column vector row vectors are mutually orthogonal, and their length is, or norm is 1. Unit vector. So this is our orthogonal matrix. Then because of this, orthogonal matrix has unique property. Therefore, yeah, I'd like to introduce. First of all, the transpose. Okay, sorry. Let's say R is orthogonal matrix. Then let's say K by K matrix. K. Yeah. Then first property is transpose orthogonal matrix equal inverse matrix of orthogonal matrix. This is a yeah, one of the property orthogonal matrix has, then which is really important. Then, so I'll explain why. So we can say transpose matrix equal inverse matrix, orthogonal matrix. So let's think about the product of Earl and transpose Earl. Then ij element of this can be written like so. Let's imagine there is matrix A, matrix B, then you think about ij elements of A, B, then if you know how to calculate the product of matrix, then so this element is multiplied by this element plus this the multiplication of this element, the two element, and so then they have their summation. So that's why if these are k by k matrix, we can write so ik means I, then this is either k. So yeah, then is, let's say this is j, then these elements are k1, k2, like that. So that's why we can write ij elements of Rn or transpose like this. That's why this can be written so RJK. So this is because like this is a transpose Earl, therefore the KJ element of transpose Earl is JK element of Earl. This is natural, right? Yeah. Then as I have said, the each row vectors are mutually orthogonal. So mutually orthogonal means if there's a vector of x and y, then the inner product will be 0. So that's why this is 0 and 1 if I call j, it's orthogonal. Then their norm is 1. If I call j, it means the inner product will be norm, right? So that's why it's 0, 1. It means this is an identity matrix. So therefore, now we can see R and R transpose equal identity matrix. Then actually in our same way, we can say this is also identity matrix. So after this event, so you can, oh, okay, oh, sorry. After this event, you can calculate this side. It's quite similar calculation. Yeah. Therefore,
sorry, Hiroshi-san, just maybe one remark. When you start at the beginning of your proof, you have R transpose equals R inverse, and the dash before R transpose, it looks a little bit like minus R transpose. So maybe you could like add like a few more lines to make it a star or something like that, just not to be confusing.
oh, what do you mean?
See what I mean? Wait, just so when you at the beginning of the proof of the explanation, yes, that's okay, that's okay. But at the very beginning of that, you have at the beginning of the line, you have like a dash.
Dash?
It so yes.
Where is?
Yes. Thanks. So that's not a minus.
Oh, but that's our inverse matrix. That's why this should be.
At the very beginning, the first character is a minus. It looks like dash R transpose. So if you read it, minus R transpose is the inverse, but no, not minus R transpose. That's not the inverse, right? Sorry, didn't want to. So this here, right? So this is just the point. Sorry,
so now it's okay. Okay. I understand. Okay.
That was just. I thought that was a little bit like yes, thank you.
That's
not a minus.
Okay. Sorry.
I was looking like why is there a minus? Sorry.
Okay. I see. So yeah, I use this mark like. So yeah. Okay, I understand. So sorry. So those are a little confusing. So there's no minus. Yeah, thank you. Okay. Yeah. So now I showed the transposed matrix of orthogonal matrix is inverse matrix of orthogonal matrix. So then, so as I have said, the distribution of X can be written like this, right? Oops. So then let's think about W. So what's gonna happen if I assign W Earl? Earl is orthogonal matrix instead of W. So it's gonna be the new W dash. So I mean, if I apply W dash instead of W, then covariance matrix is like this, right? Then this is WRO transpose plus some square identity matrix. So then now I just explained this is identity matrix, right? Because transpose Earl equal inverse matrix of Earl, not the minus. So so yeah, that's why again. Oh, sorry. Again, this is the same, W and W transpose W plus sigma squared, the identity matrix. So that's why the distribution X, it has same distribution. So whether I use W Earl or W. So that's why even though W is different based on the, I mean, yeah, the W is different due to the real transformation by orthogonal matrix, but the distribution of X will be exactly the same. So that's one of the characteristics of the probabilistic PCA. Yeah, so that's a little bit interesting, right? So because like let's think about so train this model regarding W. However, there's different W, I mean multiplied by orthogonal matrix, but the distribution is same, right? So that's a little strange property of probabilistic PCA. So yeah, this is a really related to the property of orthogonal matrix. So actually, it's a little understandable because I said in this example, so if that, so I said that, first of all, I said W is this direction. But however, let's say the W is the direction, the vector is another direction. Then the distribution will be actually the same probabilistic distribution, but of course the Z is also can be changed. But so that's a really yeah, a little bit weird but interesting topic for probabilistic PCA. Yeah. Then I think now I'd like to explain about what is the transformation with R. So what does it looks like? So I'd like to explain about that for the next. Because like it leads to better understanding for this property. So okay. So actually orthogonal matrix has another property. That one of them is linear. So okay, one of them is the so linear transformation with orthogonal matrix doesn't change the inner product. Let's say there's a vector xy, and you know the inner product of xy can be written like this. Then not change the inner product means I mean, transformed X, inner product of transformed X and transformed Y is the inner product of X and Y. That's one of the property. Then it's really easy to derive. This is the definition, right, of inner product. Then gain, this is identity matrix. That's why it's inner product of X, Y. Also, not change. Not change the norm of the vector. Actually, norm is inner product of X and X. Then what I'm saying is the norm of transformed X, transformed X called norm of X. This is also really clear. Again, this is identity matrix. That's why the linear transformation with orthogonal matrix doesn't change the inner product and norm of vector. Yeah. That's why basically inner transformation with orthogonal matrix is the rotation. For instance, this is X vector, Y vector. Then let's think about the linear transformation with orthogonal matrix, X and Y. It's gonna be rotation. Rotation means so like this. So that's why, let's say Rx will be here. Then Ry is also here. So that the angle is same. Because it doesn't change the inner product. So, okay. So inner product can be written like norm X and norm Y and sine theta. So as I have said, the linear transformation with orthogonal matrix doesn't change the norm X and Y. Then also inner product doesn't is not gonna change. That's why the angle is also same. So that's why linear transformation will be always a rotation. Yeah. Technically, there are two type of linear transformation regarding orthogonal metrics. Actually, one is rotation, and number two is reflection and rotation. Yeah, but of course, both doesn't change the inner product and the norm. That's yeah, these are the property of linear transformation of orthogonal metrics. Yeah. So therefore, so just get back to the invariance of PPCA. So I said if I assign the different W by linear transformation with orthogonal metrics, but the probability distribution is going to be same. It means, so as I have said, let's say now 2-dimension and these are 3-dimension. So in 2-dimension, the probability distribution of Z will be multivariate distribution like this. So so I mean, this is a contour. So yeah, let's say we got the sample here. It's transformed to the W. In the case W is 3x2 matrix. That's why the transformation of WZ will be the some like plane. So there is a W1 and W2. W1, W2. Then WZ will be like this. But if I assign different W, like WO, then so as I have said, the probability distribution of X given Z is WZ sigma square density matrix. So therefore, if W change to WZ, oh no, WO, then Z is changed to R minus inverse matrix of R and Z. So that's why this is again WZ. So that's why R minus 1 this is the original Z. Then let's say if R linear transformation of R is like this, then R minus 1 will be the here. So then this transformation will be WO. This is a new one. Then the result is the exact like same point. Also, you can see this as yeah, like this transform to R minus 1, then R is given back to the original, then W, then same point. So that's how it works. So I think it's a little, maybe it's a little difficult to imagine the linear transformation. But yeah, yeah, if you understand the concept of orthogonal matrix and so how it affects to the probabilistic PCA, so then yeah, I hope you understand this like concept from linear algebra, algebra side. Yeah. Then actually I programmed the probabilistic PCA. Then so how it looks like. Wait a moment. I will show the result.
Could you increase the font size a little bit?
Oh, okay.
I think just Control plus or something like that if you're on a laptop. Thank you.
Yeah. I think okay. So first of all, I prepare the sample. In this case, the related space is 2-dimension and the observed space is 3-dimension. Then Z is sample 50 samples are here. Then I set W like this. Then there's a linear transformation here. Then also there's a covariance. Then X looks like here. Yeah. Then at this time I used Stan. Stan is the probabilistic language, one of the probabilistic language. So actually today, like I skipped the detail of the program code of Stan, but so I programmed the principal component analysis I just like explained. Then I sampled the posterior distribution. Then the result is here. So interestingly, sample was the sample from posterior distribution looks like a donut, like a circle, because for the rotation of the W has the same probability distribution of X. That's why the likelihood distribution, like likelihood function, either has the same likelihood. So that's why the result of the sample looks like here. Then interestingly, I intentionally set W like this. Then this W has the biggest norm. Then this row has smallest norm. Then that's why the circle is biggest here. So then Oh, also, sorry, I should have explained. Instead, in a so as a default, it's sampled from 4 chain. That's why that's our 4 columns. But I'd like you to check for this like 3. This is our first rows and second rows and third rows. In the same way, the latent space, the Z is also looks like circle. So it's a little weird. Then actually, when you analyze the data with principal component analysis, you have to specify which direction. Then actually, there another technique for that, but I will skip that topic for this session because like it takes lots of time to explain. So that's why I skip. But so in this session, so I just wanted to explain the property of orthogonal matrix and how it affects to the probabilistic principal component analysis. Yeah. So yeah, if you enjoy this property or like this presentation, yeah, I'm really glad. But yeah, so this is a full presentation, my presentation today. So thank you.
Thank you, Hiroshi-san.
Thank you so
Hi.
much.